to the series of lessons on Advanced Calculus 2, Vector Function. This is the first section in this series of videos. In this section, we shall look at the definition of vector function and the domain of vector function. What is a vector function? A vector valued function, or simply put it, a vector function is simply a function whose domain is a set of real numbers and whose range is a set of vectors. Is a function whose domain is a set of real numbers and whose range is a set of vectors. Good. A vector function can be represented as r of t is equal to f of t I plus g of t j plus h of t k. The f of t, the j of t, and h of t becomes the component of this vector function r of t. And since they are defined in the form of functions, the f of t, g of t, and h of t are best described as component function. Remember, when we compute f of t, g of t, and h of t, the output will be real numbers. But the combination of them, as shown here, becomes a vector form. So we say the domain, the numbers we input into the function, are real numbers. But the output, which will be in the form of I, j, k, will be in vector form. Remember, vector functions are mostly in the 3D space, or they are three-dimensional vectors. For instance, we can have a vector function such as r of t is equal to t cubed t squared plus 1 t squared minus 1. So where t cubed, t squared plus 1, t squared minus 1 are all functions, and they represent the component of this vector function. And since they are functions and they are still components, they are best described as component functions. The t is a parameter of this vector function. So the value of our vector function will depend on t. So for instance, when t is equal to 2, r of 2 will be equal to 2 cubed, then 2 squared plus 1, then 2 squared minus 1. And this will yield 8, 5, and 3. So the 8, 5, and 3, which is the domain of this vector function, are real numbers. But a combination of these three, which represent our RT, is a vector. That is why we say a vector function is simply a function whose domain are real numbers, but the output is vectors. So the range, which is the output, our vector, a set of vectors. Good. Now that we understand what a vector function is, we shall look at how to find the domain of a vector function. Remember, for every function, we have a set of elements that forms a set of numbers that form a domain. So we are now going to learn how to find a domain of a given vector function. The domain of R consists of all values of t for which the expression for R of t is defined. So for instance, we said R of t is equal to f of t I plus g of t j and then h of t k. So the domain of this function will be set of all real numbers that will make these three functions define simultaneously. Remember, the functions, the real numbers, and considering the functions g of t, g of h of t, and then f of t, certain numbers will be defined for one function and may not be defined for the other function. So looking at the combination effect, the numbers or real numbers that will make the three functions define at the same time. So the intersection of f of t, the domain of f of t, g of t, and h of t becomes the domain of R of t. So when we ask to find the domain of any vector function, we look at the individual component functions and look at the numbers that will make the individual component functions define. Once you know the, the numbers that will make the individual component function define, then you compare them and select their common ones, the numbers that is common to all of them, that will represent the domain of the vector function. Let's make an example. We have to find the domain of the vector function R of t is equal to t cubed and ln 3 minus t the square root of t. So the domain of this vector function will be all values of t for which the three functions t cubed, ln 3 minus t, and the square root of t are all defined. So first and foremost, we will look at the individual component functions. What is the domain of those individual component functions? Once we have gotten that, then we can compare the three domains and pick the one that is common to all of them. Those element that is common to all of them becomes the domain of the vector function R of t. So let's start with the first one. The first one is t cubed. What is the domain of t cubed? The domain of t cubed are all numbers of t that makes the function t cubed define. And t to the power 3 is defined for all real numbers. So all real numbers satisfy the function t cubed. Let's pick the second one, ln 3 minus t. The ln function is defined for numbers greater than 0. So this implies ln 3 minus t can only be defined when 3 minus t is greater than 0. Or otherwise, t3 is greater than t. And more precisely, we can say when t is less than 3. Remember, when 3 is greater than t, then it's very obvious that t is less than 3. When something is greater than something, then the other thing should be less than 3. So if 3 is greater than t, then t should be less than 3. So the length function here will only be defined when t is less than 3. Good. Let's pick the square root of t. The square root of t will define if only the value of t is non-negative. It's a non-negative number, or otherwise greater or equal to 0. Remember, we are working the real number space, and the radicals sign is defined on 0 and positive real numbers. So t, the domain of this function square root of t, is defined when t is greater or equal to 0. In order to find the intersection of these three domains, the intersection of the domain of these three functions, we will use the number line. So this is our number line. The first one is all real numbers. All real numbers. So everything on the number line is defined for t cubed. Then the second one is defined when t is less than 3. So assuming 3 is here, we can also illustrate that with an arrow pointing to the left, less than 3. So this is the function len 3 minus t. So this represents the domain for the function len 3 minus t. Let's look at the other one. The other one, t should be greater or equal to 0. Greater or equal to 0. We shade here. The arrow points to the left. So we look for the intersection of these three regions. The intersection of these three regions graphically will be here. So to illustrate our final answer, that will be from 0 up to 3. So we can write this as 0 less or equal to t less than 3. Or square bracket 0, then 3. Open at 3. So this represents the domain of our vector function. Let's look at another one for better understanding. We have to find the domain of the vector function r of t is equal to t raised to the power 4i plus the square root of t minus 3j plus 8 minus the square root of 8 minus tk. So the domain of t raised to the power 4 is all real numbers. All real numbers. Then the domain of t minus 3 will be numbers that will make numbers of t that will make this expression t minus 3 0 or positive. 0 or positive. So this implies t minus 3 should give us 0 or a value greater than 0. So t minus 3 should be greater or equal to 0, which implies t should be greater or equal to 3. Then the last one, 8 minus t, the square root of 8 minus t. The domain of 8 minus t are all numbers that make 8 minus t greater or equal to 0. This implies 8 is greater or equal to t. Better still, t less or equal to 8. When 8 is greater or equal to t, it's obvious that t should be greater, less or equal to 8. So let's use the number line to help us find the intersection. So the first one is all real numbers for t. This is our number line. Sorry. This is our number line. So all real numbers for t raised to the power 4. T raised to the power 4. The function t raised to the power 4 is defined for all real numbers. Then the second function, the square root of t minus 3, is defined when t is greater or equal to 3. Is greater or equal to 3. So this is the square root of t minus 3. Then the last one, t should be less or equal to 8. T should be less or equal to 8. As the square root of 8 minus t. Then we look for the intersection of these three domains. The intersection of these three domains is the shaded region here. So quickly, we can represent this on the number line as from 3 inclusive up to 8. And this can be written as 3 less or equal to t less or equal to 8. Or otherwise, 3 close at 3 and opened, and closed at 8. This becomes a domain of our vector function. The domain of our vector function. Let's look at more examples. So we shall look at this exercise. We have to find the domain of the following vector functions. So let's pick the A. The component functions are t squared, the square root of t minus 1, and the square root of 5 minus t. For t squared, its domain is all real numbers. For the square root of t minus 1, the domain is when t minus 1 is greater or equal to 0, or otherwise, t is greater or equal to 1. Then the square root of 5 minus t is defined when 5 minus t is greater or equal to 0, or 5 is greater or equal to t, or better still, t is less than or equal to 5. So let's use the number line to find the intersection of these domains. The first one, t raised to the power 2 or t squared, is for all real numbers. So this is for all real numbers, t raised to the power 2 or t squared. Then the second function is the square root of t minus 1, which is defined on t greater or equal to 1. So if 1 is here, t greater or equal to 1 will point this direction. Then the last function is the square root of t minus 1. Then the last function, the last component function is 5, square root of 5 minus t, and is defined when t is less or equal to 5. So t square root of 5 minus t, and this is defined when t is less or equal to 5. The intersection will be from this point. So this will be the intersection. This region with the intersection of the three domains. Can represent that on the number line as from 1 to 5 inclusive, or 1 less or equal to t less or equal to 5, or better still, square bracket 1 comma 5 then close with a square bracket. So this is the domain of our vector function r of t. Let's look at the last question, the B. We are to find the domain of r of t is equal to t minus 2 on t plus 2i plus sine tj plus 9 minus t squared k. So the first vector function, component function, is t minus 2 over t plus 2. And we know that this expression or this function is defined if t plus 2 is not equal to 0. This implies t can never be equal to negative 2. So the first function is defined for all real numbers except negative 2. And then sine t. The sine function is defined on all real numbers. All real numbers satisfy sine t. So you should understand the various functions and how they behave. The len function, the trig functions, the log functions, and etc. So that when they are used to define a vector function and you are finding a domain, you'll be able to find the domain very easily. The sine function is defined for all real numbers, and as such, the domain for sine t will be all real numbers. The len is always defined on positive numbers, numbers greater than 0. So the domain of len 9 minus t squared will be 9 minus t squared greater than 0. 9 minus t squared is greater than 0. Let's look at how to handle 9 minus t squared greater than 0. Remember, this is a quadratic inequality, what I've just written. 9 minus t squared greater than 0 is a quadratic inequality. The way we handle quadratic inequality is not like how we handle quadratic equations. So first and foremost, we have to find the root of this quadratic inequality. So we'll convert it to an equation and find the roots. So this is factorizing this difference of 2 squares. This will be 3 minus t, and then 3 plus t is equal to 0. This implies the roots are t is equal to negative 3 or 3, positive 3. We'll now use the number line to find out range of numbers that will satisfy the quadratic inequality 9 minus t squared greater than 0. And this is best achieved by first drawing your number line and putting your roots on the number line. There are 2 roots, so negative 3 and 3. Once we put the roots on the number line will be divided into 3 portions. So let's call them region. We'll call them region A, region B, and C. Region A represents numbers that are less than negative 3, less or equal to negative 3, to infinity. Then region B, numbers between negative 3 and positive 3. And then region C, numbers beyond 3 up to positive infinity. So these are the 3 regions. And with quadratic inequality, when the region A satisfy, numbers in region A satisfy the quadratic inequality, it is automatically that the region C will also satisfy. So region A and C are always linked. So when region A and C satisfy, the B will not satisfy. And when the B satisfy, the region A and C will also not satisfy. Good. How do you know that which region satisfy? We can find the region that satisfies our quadratic inequality by picking a possible number within the region and test it to the quadratic inequality. For instance, let me test region B. Region B contains a possible number such as 0, from negative 3 to 3. Possible numbers include negative 2, negative 1, 0, 1, 2. So I'll pick 0. That will make our calculation more easier. So let's do that on the next page. So when t is equal to 0, we'll have 9 minus 0 squared greater than 0. We want to test whether it's greater than 0. And 9 minus 0 squared will have 9 greater than 0. So when t is equal to 0, our quadratic inequality is satisfied. So it means region B satisfies our quadratic inequality. And as I said earlier on, when region B satisfies, then A and C will not satisfy because A and C move together. And when region A satisfies, C also satisfies, but B will not satisfy. To make this one clearer, let's even test region A and C. So let's pick a possible number that can be in region A. Region A, we can have a possible number such as negative 4 because region A are all numbers less than negative 3 up to infinity. So let's just pick a simple number such as negative 4. So we have 9 minus negative 4 squared. We are going to have 9 minus 16, and that will give us negative 7. I hope I'm correct. Yeah, negative 7. So we can see negative 7 is not greater than 0. Negative 7 is not greater than 0. So this is for region A. Let me even indicate that. Region A. When t is equal to -4, region A, when t is equal to -4. So it doesn't satisfy. -7 is not greater than 0. As I said earlier on, the region C will also not satisfy. But for clear understanding, let's test the region C. A possible number in region C include, let's say, 5, because region C contains numbers that are greater than 3 up to positive infinity. Region C, when t is equal to, let's say, 5, the example is 5, we're going to have 9 minus 5 squared, and we're going to have 9 minus 25, and 9 minus 25 will give us a -16, -16, -16. And we know -16 is not, this is not greater than 0. So it doesn't satisfy our quadratic inequality. So the only region that satisfies our quadratic equality is B. So the domain of this quadratic inequality can be represented graphically as from -3 to 3. Remember, it should be greater than 0, not greater or equal to, so we will not shade the circles here to be open. So now we are going to combine these 3 domains. Remember, this, what we have just done, is the domain for the length function. So we are going to combine these 3 domains for us to find out the common values of x for t, for which our RT is defined. So we'll combine this with the results of the all real numbers and the results we obtain from this quadratic inequality. We shall do that using the number line. Okay, so let's proceed. So we'll draw our number line. The first one is t not equal to -2. So if -2 is here, we can represent that as this: all real numbers except -2. So this is for the first function, which is t minus 2 over t plus 2. This is the domain graphically. And the second one is all real numbers. That's the sign t. All real numbers. Sign t. Then the last one is from -3 up to +3. So -3 somewhere here, +3. It is open at -3 and still open at 3. So this graphically represents length 9 minus t squared. Let's look at the intersection. The intersection will be from here, and there will be a jump. There will be a jump at 2 up to 3. So graphically, I can represent this as -3 up to -2. There's a jump here. Then up to 3. So we can see that this will be two domains joined together. So this is going to be -3 less than t less than -2 union -2 less than t, less than t, not equal sign, less than t less 3. Or we can use -3 comma -2 close, open union -2 comma 3 and also open. So this will be the domain of our vector function R of t. So this is the end of our first session on vector function. This section we have looked at what a vector function is. We have also looked at how to find the domain of vector function. See you in the next session. Remember to subscribe to my channel. Thank you.